So I'm going to be taking you through SimSolid in this part of the webinar. Now, for those of you who haven't used it before, or for those of you who have, same again as the last session that I did, we're going to go through the capabilities and benefits of using SimSolid. You'll then see a demo of the software, and obviously we'll address any question and answers at the end that you might have. Again, SimSolid is part of our simulation-driven design suite. So with your traditional FE processes where you have your part, you then need to defeature it. You need to make sure that you have good CAD, you would clean the CAD up, and then you would then probably, go through quite a labor-intensive method of meshing everything up. Now, with SimSolid, it basically uses a new technology that operates on your original unsimplified CAD geometry directly, and it doesn't need you to create a mesh. And you get your results within seconds to minutes. So if we're going to compare between the traditional FE process, that'll be the top bar at the top here, where a lot of time is invested into the pre-processing of it. I'm sure you guys have gone through, the pains of you bring CAD in, it might not always be perfect, so then you're sat there cleaning the CAD up, you're making sure that all of your surfaces are connected properly, and then after you've done that, you then need to make sure that you give it a mesh that represents your geometry well enough and that it's a good quality so that you won't get rubbish results. And then the solve itself will probably take a little while to run, and you'll probably need to fight with other of your colleagues to make sure you get a license or to make sure that you get to submit it on the HPC in time. But then after that, you then have time spent on the post-processing of it, so the analyzing, the understanding of the stresses, and the way in which your whole assembly works together. Now, with SimSolid, the biggest difference in it is that you don't need to do any of the meshing, and you don't need to tidy up the CAD either. You bring the CAD in, SimSolid will know exactly how to handle your geometry based upon the setup that you've given it. So where you start constraining it, where you apply your loads, it will understand exactly where it needs more refinement and where it needs less refinement on. The solve itself, because of its new technology and the type of elements it's meshed itself with in the background, what the solver does is that it applies a high order integration equations on your a high order differential equations on your different parts of your structure in order to be able to calculate the stresses and strains and displacements at those different parts of your CAD. So that's the technology behind it, and that's different to the traditional, force equals KU, the F equals KU sort of formula that we're looking at. But then the post-processing of once you actually have your SimSolid results, that's all the exact same as you would have done previously. So where you can then start recording videos, you can take pictures, and you can export all of these values out as a table. And what this means is that the moment you reduce the amount of time it requires to mesh or to clean your CAD, it's a quicker and shorter process. So this gives you a lot more opportunities to run numerous additional studies, and it gives you a significant impact in the early design phase. So yet again, reiterating what we're talking about in the whole simulation-driven design phenomenon. So the way in which it works, like we said, in the new technology, it's meshless, so you don't need to do any of the meshing itself. And on the original CAD geometry, what it will do is apply those high-order differential equations. It works in high capacity, so you're not limited to looking at just the one part. You can look at a large assembly of different complex parts as well. It is accurate, so just because it's quick does not mean it's dirty. It goes through a multi-pass adaptive process, and it uses these smart functions in order to adapt itself so that it's giving the right stress value that you need it to be. And just so you know, it is very fast in solving. You can look at the speed and the scalability of it, and you get your results in minutes. You also don't need any sort of special hardware investments into it. It will just work straight off the bat using laptops, so you don't need any sort of high performance computing in order to solve for it. Now, the way in which SimSolid works as well is that you can use it with an assembly of big, small, thick or thin parts. You're not just limited to looking at the one type of results. You have you may have small geometry features inside your CAD itself, and you can keep all of these different small geometry features like pinholes or small fillet radius. You can keep them all in. You don't need to take them out because they don't cause singularities in your results. In the event that you might not always have perfect CAD, where you have part gaps and overlaps, you can actually keep all of these in. SimSolid is very forgiving, and it'll be able to keep these parts in for you. And it won't affect your results either in terms of the stresses around these imperfect contact areas. You can also start looking at extreme geometric complexity. So if you want to bring in any lattice structures, any scanned data, you can also simulate your stress analysis using these kind of inputs. And where you might need to use odd face transitions or small splinter surfaces in the drawing of your CAD, this doesn't get affected in your results either. So you won't see lines of meshes around these focus areas, and you won't get singularities again. So the benefit of SimSolid is the fact that you get a fast pace of design. The required time to solution would be minutes instead of days. You can deal with high geometric complexity with it as well, and you can deal with large assembly sizes. And all it requires is just 3 simple steps to get to that endpoint. In the modeling, when you bring your CAD geometry in, it will process your geometry, it will classify it as well, it will create the connections that you need for you, and it will also create your analysis parameters so you can specify exactly how it's being held, how it's being loaded. You also have the solving process where it will go through and it will then implement the mesh in the background for you. It uses a different type of element, and like we said, the higher order differential equations. And in the end, you have your results. So with the results itself, you can always get the same type of results from the analysis that you've implemented, whether if you're looking at displacement, stresses or strains, a modal analysis. You can also display the reaction forces and where it's being held. And you can always couple it up with a fast reanalysis. So if you wanted to change a small parameter, you can, and it will solve very quickly. And there's also an efficient coupled analysis. If you wanted to couple up your structural to a thermal analysis inside of SimSolid, you can. Now, these are just some of the known features in SimSolid that we're looking at. So like we said, you can look at statics as well as dynamics in SimSolid. Now, you can look at a modal analysis, and after the modal analysis, obviously you can take it through for a frequency response or random response as well. But then if you want to look at a structural, you have your linear and the non-linear side. You can look at thermal and any other sort of non-linear phenomenons like inertial relief or bolt pretension. You can include all of those in. And last but not least, you can also start looking into fatigue as well in SimSolid. Now, the types of materials that you can work with is the fact that obviously you can deal with your isotropic metals, plastics. You can also start looking at elastoplastic too. So where you want to start looking at bringing in the non-linear curves of your materials, you can bring all of that in. You can make different parts rigid. So if you know that they'll never deform, you can keep it as rigid. And one of the newer aspects is the fact that you can bring in orthotropic materials if you want composites. And you can also start looking at fatigue with the right stress strain and strain life curves as well. In the connections that you want, obviously in my tutorial later on, I'll be showing you how you can weld a frame together very quickly with the connections tool in SimSolid, but just know that you do always have the option to do auto connections, and from that auto connections, it will give you bonded, sliding, or separating with friction. You can start looking at bolts, where you might want to incorporate bolts into them, any sort of pretensioning in them. You can bring in spot welds and seam welds and any sort of virtual connectors. If you want to do a remote connection type, you can. You can incorporate adhesives and joints as well. Now, last but not least, in terms of the results, like we said, if you're conducting a, let's say, a modal analysis in this aspect, what you will find is that you always get the same set of results from it. So you always get your frequencies and mode shapes, and you always get the modal participation factors from it. Say if I wanted to look at a linear static analysis, from there I'll always get my displacements and strains and stresses, and I can always get them in the form of XY plots. I'll get my forces and my bolts, and obviously you can look at everything in terms of a contour and animation. And the post-processing side, you can look at the minimum and maximum labels, safety factors, and bookmarks. So just so you know, in terms of the forces, such as your contact forces or the forces that are going through your bolts, you can always get these in a form of a table. So if you want to export it, and if you want to, post-process it in Excel, you can. Now here's just a few of the customer stories we have. Like we said, SimSolid is this, we call it new technology, but to be fair, it's been around for many, many years. And, loads of our clients are using it. It's accurate, it correlates to the physical tests, it works, and it's fast. So at this point, we're going to play the video, and after the video, I'll address the questions that you guys are writing up. Hello again. So I'll be taking you through looking at SimSolid and showing you exactly how you can get your results within seconds of importing your CAD into the software and understanding exactly how it's performing immediately. So at the end of this video, I'm hopefully going to be able to show you how you can take or bring in your own CAD, bring in your own frame structures, implement some connections on it, such as welds, and then you can assign a load case to it to then understand exactly how it's performing. Now for those of you who never heard of SimSolid before, I have done a previous video of this. It is on YouTube, and one of the main differences in that video is that it goes through a lot of your different user control options and how it is that you can directly implement your new sort of CAD designs. And what it does is that SimSolid will then take your original design study, creates a new design study for you with all of your load cases mapped over so that you don't need to go through that process again. So it's great for looking at quick CAD iterations, whether if your CAD changes have improved your design or not. Whether if your different CAD iterations have improved your designed parts, and you can see exactly the stress levels around each of the parts itself and displacements. And SimSolid does all of this for you seamlessly and in an incredibly user-friendly manner. So let's not dwell. I'm going to show you exactly how you can bring your CAD in, and you can then set it up for a load case like this, implement some welds that you see that you can generate for your different parts, get some stresses in those parts as well, and understand how it's performing. So you'll see that at the moment we click on the play button, we can see the way in which it deforms, its deformable shapes, and the manner in which it's being used in. So let me close off this session. Now, within SimSolid, again, it is CAD agnostic like all of our other softwares, meaning you can bring in any sort of CAD format you need. You don't need to put it in a specific file format. It can read in everything, including the native CAD formats from your different CAD packages. So what we'll do is at the moment we bring this in, we'll see that it creates a new design study, and within that design study itself you can see the assembly associated to each of these. So the assembly of your different parts. Currently it doesn't have any connections at all, and it's got one structural analysis assigned to it, but I can delete that for now. So let's start off with just the basic CAD. Now in the assembly itself we can look at applying a material to it, because obviously with all our parts we need to assign a stiffness value in order to be able to calculate a finite element analysis on it. So within SimSolid, what we're going to do is let's just assign steel to all parts. Close, and once you see that that steel has been assigned, you'll see that a material will be assigned to the end of these different part names, so you know exactly what material everything is. Now if you're working with a huge assembly of parts, you can always check for unassigned materials by simply clicking on, or unassigned parts by simply clicking on show, right click on assembly, show parts without materials, and if everything has been assigned properly then it will tell you that there are no parts without material assigned. Now the workflow we also recommend is that if you know you have an amalgamation between welded parts as well as bonded contacts or connections that you want to implement in, we always recommend doing your welded contacts first. So within SimSolid you can create spot welds or seam welds or adhesives, just so you know that you do have lots of different virtual connectors that you can also use. Now say if I wanted to create new seam welds, You would specify your section size and the minimum length in where it is that you want to implement a weld upon, and there's so many different ways in which you can do it. For now, I'll just do a group weld, and what I will do is hold down Shift to do a box select of my different parts. Sorry, hold down Control, do a box select of all my parts, and then at this point what we're going to do is click on Find Welds, and you see very quickly it would have found lots of different welds. Total number is 212, but what you can then do is then zoom in and see exactly where all these welds have been placed in your structure. And whichever one is highlighted, so say if I highlight number 17, we don't know where it is in this big assembly, just click on this magnification icon and it'll show you exactly where weld 17 is. Once we're happy with that, click on OK, and you'll see very quickly SimSolid's already done all of your seam welds for you. Now at this point here, we can also use this button. You'll see that where you click in your project tree browser, if you click on Assembly, you have the Assembly Workbench toolbar. If we click on Connections, we then get the Connections Workbench toolbar as well. So just so you know, with this button here, if you click on it, it will show you if you have any disconnected group of parts, and what it should tell you is that you have no disconnected group of parts at this moment. Great. So once we've done this, what I also want to show you is that this main top toolbar up here, within my other video on YouTube, it will go through all of your different user options that you can go through, the way in which you want your CAD to be displayed, how to hide parts and show different parts, and your different selection tools. But what I will focus upon in this video is the fact that with this end set of buttons would be the different types of analysis that you can conduct. Within SimSolid 2021, we can start looking at structural linear and non-linear. We've always been able to do this. We can specify to look at a modal analysis, dynamic analysis, so whether if it's a transient analysis, frequency response or random response. You can also conduct some thermal analysis as well, but within 2021 you can also look at fatigue, whether if it's stress life or strain life, whether if you want to check for the life cycles that your part can endure, or just the damage that it undergoes. You can conduct fatigue within SimSolid. But for this tutorial, just this example, I'm going to conduct a structural linear for now. And within structural 1, the moment you set up a load case, you see you have your load case workbench toolbar. And at this point, if you click on immovable, I'm just going to specify that I want all of my bottom faces to be constrained in all degrees of freedom. Now as you go through and click these different faces, if it's easier for you, you can click to have your edges showing, so that's easier to see. If it gets to the point where you don't remember which faces you've selected, you can always do a shift select to see if you've missed any out, and you'll see that I've missed out this corner and this corner. So now if I do another shift select, we can now see that I've highlighted all of my bottom faces properly. So I'll click OK. You can see my constraints are there with these yellow crosses. For the next part, I then want to implement, let's say, a force to act on the top surface of my frame. Same again, we can go through and let's say if we do add tangent faces, if I click on this one face, you'll see that it'll apply to everything around it. So if that is something that you want to do in, let's say, your frame or a chassis that you're looking at, then that is an option that you can tick without having to go through everything. But it's not what I want to do for today, so what I'm going to do is just go and click through each of these individually. And same again, I can go through and click on these different top faces. Now you also see that within SimSolid is that you don't have the option to edit your CAD or your geometry the moment you bring it in. So what I did want to make you aware of is the fact that you can use spots. So say if it wasn't the whole surface you want to apply the force to, but instead just a tiny square surface on this area. Now what you will be able to find is that with spots you can specify exactly the area in which you want to implement spots upon to actually apply your load cases to. So just so you know, that is another option that you can use. And now let me do a shift select to make sure I've got all of the top faces that I needed. Once that's correct, what we're going to do now is head over to looking at our global axis. We want to have a downwards force in Y, so that would be negative, and let's specify negative 10,000 newtons. And once we're okay with this, just click OK. We'll see some pink arrows showing up, and we can solve for it this way. Now if I click on, just so you know, you do have other loading options as well. We won't be touching upon it, but you can use enforced displacement. So if you're trying to replicate real test data and you don't have the forces behind it, you can use an enforced displacement to emulate that distance traveled. We can apply inertia loads, gravity loads, so any G loads that you want, any inertia relief. You can do remote loads, bearing loads, hydrostatic pressures, etc. So if I were to click Run right now, you'll see the bottom left corner is where your software is talking to you and telling you exactly what it's going through in the solving phases. And within seconds of clicking Solve, you already have your results. So if I now look at my von Mises stresses, I can click for play, and we can see exactly how it's displacing by and where our maximum stresses would be. We can click on the min-max values, and you can see that the maximum stress occurring right now is actually at the back part here, acting upon a weld in itself. And say if you wanted to, dramatize your contour plots, you can always adjust these accordingly. So let's make this 5, and let's make this one 0. So you can see which areas undergo most stresses. And let me reduce this down a little bit. I realize that my loading is quite low compared to the rest of the strength of this frame. And you can see anything that exceeds over, let's say 1 in this instance, we can see exactly which areas are most stressed. You have your usual options at the side here where we can increase the oscillation of your animations, how continuous and discrete your animation is as well. So if you want it to look more robotic, then obviously it'll be less continuous, and the more continuous it is, the smoother it looks. It could be that you wanted to hide off all of your contacts. So say if I go into connections, we can hide off our seam welds. So if I do hide all, and now if I go back to displaying the results of stresses, we can see that the maximum stress on the actual beams of our assembly is only around 1.3 megapascals. Now at this point here, like we said before, if you do any CAD changes, just simply do project and import from file, bring in your new CAD iterations, and everything will be mapped over for you. You can watch my previous video to see how you would do that. But with this one again, what we can always do is if you simply right click copy, you'll see it pastes that structural 1 load case into a structural 2 load case, and you can easily vary it to see exactly how high you can load it up before it starts yielding. So I can do that in this way. I can also then again, let's do another copy and paste. I can then change it so that instead of this value, I can put it so that it acts in the X, Y, or Z value, however you want to set up your different load cases. But I can delete that one off and simply just add in a modal analysis as well. And within this modal analysis, again, we can copy and paste it. But what's nice is that, let's say if I take this immovable constraint, I can copy it to a certain load case as well. So I don't have to copy and paste whole load cases. I can take one aspect, such as that constraints there, so that I have one free modal analysis and one fixed free modal analysis. And once that's all done, I can simply just click on the whole design study, and I wanted to solve for everything. And you'll see whichever one's highlighted in bold is the one that it's solving right now. And within a couple of seconds, throughout every time it solves, you can see how quickly it goes through and gives you the results that it needs. So every time you have a set of load cases with results, a new icon would show up saying result, and you'll have the results that you need for each of them. Now, just because it's fast is by no means is SimSolid an inaccurate or dirty solver. We've done plenty of internal benchmarks to validate its results, and you can visit NAFEMS online or access the NAFEMS article to look at a benchmark that they did between SimSolid and all of the fully advanced, traditional FEA solvers as well. And last but not least, it's now finally solving the fixed free analysis. And once all of these are done, you can go through and click on the results to analyze them and understand exactly how your parts are performing. Okay, so once this is done, we have these results here. So if I go through and just go through each of these results, now we can see, let's look at displacements. Now you'll see there's also live synchronization between the window screen, and say if I was to click on structural 2 immediately, it will show you the same type of displacement contour plot, but for the different structural load case. So very quickly you can flick between the two to see the differences between them in results. And obviously, as we expected, the loading in structural 2 is 100 times greater, hence you can see that in the results as well. And say if we then went through and clicked on the stresses, same again, because we've hidden off all of our welds, we can see now the maximum force, the maximum stresses occur in the same location. With the modal analysis, like we can see here, the first 6 ones in our free analysis would be our rigid body modes, so how it would displace and rotate in degrees of freedom X, Y, and Z. And then when we go through to start looking at its actual natural frequencies, you can see whether if you have your bending modes or if you have any torsional modes instead. And same again for the modal 2, because we actually constrained it as now a fixed free analysis. We no longer have your first 6 rigid body modes, but instead you get to see the natural frequencies, whether if they're bending or whether if they're torsional modes. And say if you wanted to conduct this whole analysis again, but changing the material of the part you're using, you can do it very simply by just simply right-clicking on Design Study 1, copying it, and you can see it's copied everything over into Design Study 2. But what you could change very quickly is just Assembly, and let's assign aluminium to all parts. And you'll see once we have all of these aluminium parts here, we can tell it to solve for it again. And these can be the different design iterations that you might want to look into. And last but not least, I'm just going to show you the quick processing of this as well. When you have a moving animation, just click on the camera icon, and because it's moving, it knows to save it automatically as a video. Let's say we're actually looking at, let's make this a bit more dramatic in terms of the scale deformation, and let's say this is the angle that we care about. It's no longer a moving animation. If I take a snapshot, it knows to save it as a still picture format. So very quickly you can right click and save media to files, and then it exports it all out in the correct format you need for you to put it into reports, PowerPoints, your Word documents for quick reporting. And this is pretty much how you can use SimSolid for rapid structural analysis in any of your different design processes that you might want to use. Thank you for listening. Okay, so hopefully everyone had a really good understanding in how it is that they can incorporate SimSolid into their workflows, the benefits of it, and just the speed at which you can get results from it. So what I'm going to say is that with SimSolid, the recommendations around it is the fact that you want to import only your solids, don't bring surfaces in, and make sure that your solids are properly closed, so no open solids with it. And just make sure that you keep it to your high fidelity CAD models. You don't need to worry about defeaturing it or anything. Just keep it as it is. And just so you know, you can work with CAD as well as STL, so any scan data that you have, but just be careful because obviously with scan data, it will assume all of it as one surface. So just make sure if you can bring CAD in, just bring your CAD in if you can. Use your CAD geometry as is. So where you have pinholes and everything, don't feel like you have to remove them. And where you're actually working with large assemblies, that is completely fine. Don't worry about having to simplify it down by merging them together or assuming that they're one part and specifying like a boolean between your parts. You don't need to do any of that. Just bring your large assemblies in as they are. So in conclusion, obviously we know for a fact that SimSolid isn't just tied down to the one sector either, like with all of our products. You can look at them from a construction form or from a biomedical form. Now, it is super game changing in how rapid your design iterations can be if you were to use this. It gives you a seamless workflow, and it's got a very easy to use GUI as well for you to interact with. It's very user intuitive. It also eliminates any sort of geometry simplification and meshing that you might need to do. So if you just need a quick result, just use SimSolid. It helps you analyze complex and large assemblies. So you're not just limited to looking at the one part, you can bring in thousands of parts in, like the example that Jan showed earlier, that stage, that elevating stage, that's got more than thousands of parts inside of it, and it solves super quickly. And like we said, just using a standard PC or a standard laptop, you can get your results in minutes too. And like we said before, there is a NAFEMS article on SimSolid. So before we, obviously, when we were developing SimSolid, we always make sure that we did our own internal benchmarks, and we did it heavily from comparing SimSolid to OptiStruct, which is our full-blown structural solver as well. But then external parties like NAFEMS, if you haven't heard of them, you know, NAFEMS are like a governing body of looking at finite element analysis as well as all simulations to make sure that the tools that the engineers in the world can use are safe and reliable. And NAFEMS did a benchmark where they did it, where they looked at comparing SimSolid against their fully advanced CAE solvers as well, and you can see that the discrepancy in the results is less than 1% for most of them. The biggest difference is only 4.2%. So if you do want to look at the article, do let us know. We can upload it here again as well for you. But thank you very much for listening. I'll take any questions that you have now.